these are all desirable, then why not have large amount of subcooling? Ultimately, unfortunately, there are certain constraints. What are the constraints? The degree of subcooling depends on the extra area provided for heat transfer and the temperature of the heat sink. So if you are trying to provide subcooling by increasing the area of heat transfer, obviously you are incurring additional cost because the heat exchanger becomes bigger, so additional cost. Okay. At the same time, it is also limited by the temperature of the heat sink. As I have mentioned already, the exit temperature of the condenser cannot be lower than the heat sink temperature. Okay. So that ultimately the degree of subcooling that you can get by this method depends upon the extra area you can afford to provide and the heat sink temperature. Okay. Now let us look at the other modification, that is called as superheating. What is superheating? So temperature of heat source will be a few degrees higher than the evaporator temperature. Hence the vapor at the exit of the evaporator can be superheated. This is again similar to your condenser problem. If you want to exchange heat from the refrigerated space to the evaporator, you must provide certain delta T. Okay. A typical example, for example, if you want to maintain your freezer compartment of a domestic refrigerator, let us say at minus 18 degrees centigrade, then you have normally they operate the evaporator at about minus 23 degrees centigrade. That means about 5 degrees of temperature difference is provided so that heat transfer can take place in a finite area. Okay. So some delta T exists. So if you are if you can afford to, you can add more area and you can reduce the delta T, keeping the pressure constant. Okay, thereby what you are doing, you are adding extra area for heat transfer, there will be higher heat transfer to the refrigerant, thereby the exit condition of the refrigerant vapor goes into the superheated region. Okay, so just like your subcooled this thing, this will go into the superheated region. So this is what is known as the superheating. Okay. Now superheating can be, unlike subcooling, superheating can be useful or useless. What do you mean by useful superheating? If the superheating of refrigerant takes place due to heat transfer with the refrigerated space, then it is called as useful superheating. Okay. That means if this heat transfer is taking place inside the freezer compartment, okay, then it is useful because the cooling effect is ultimately given to the products. Okay. So it is, you call it as useful superheating. On the other hand, if the heat transfer is taking place outside the refrigerated compartment, let us say that it is exchanging heat with surrounding air, okay, then you do not get any benefit, right. So the refrigerant gets superheated, but you are not getting any benefit. Okay. This kind of a superheat is known as useless superheating. Okay. So as I said, on the other hand, if refrigerant vapor becomes superheated by exchanging heat with the surroundings, it is called as useless superheating. Let us look at the effect of useful superheating. For the let me tell at this point, and I will also show this later, but useless superheating is detrimental to system performance. Okay. So as far as possible, a system should be designed in such a way that whatever superheating takes place, it takes place in a useful manner. Okay. So all useless superheat should be avoided. So let us look at the effect of useful superheat. Okay. So this figure shows again, just like subcooling, the cycle without and with superheating on TS as well as PS diagrams. Okay. Look at the TS diagram, as I said 1, 2, 3, 4 is without superheating. Okay. If you do not have any superheating, what is the your useful refrigeration effect? This is the useful refrigeration effect. Okay. This area, right. And what is the work of compression? We have seen that the work of compression in fact is this entire area. Okay. So this is QE and this is your work of compression without superheating. Now let us say that I have superheated it. Superheated means what I am doing? I am pushing this exit condition from the saturated vapor to a superheated vapor, okay, along the constant pressure line. That means this is the constant PE line. Okay. So it is a sensible heat transfer process, assuming that there are no pressure drops, so it is taking place isobarically. So this point is shifting to superheated region. Remember that you have subcooled region here, two phase region here, and superheated region here. Okay. So because of this superheating 1 to 1 dash, okay, so 1 to 1 dash is your superheating. So what is the effect of the superheating? First effect, immediately you see that there is an increase in refrigeration effect, and that increase is given by this area. Okay. So this is the area which is an indication of increase in refrigeration effect because of superheating. Okay. And there is also another effect. What is that? There is also a simultaneous increase in work of compression, and that is given by this area. Okay. So because of the superheating, both refrigeration effect as well as the work of compression both are increasing. Okay. The same thing can be seen from this point also. Without superheating, from pH diagram, without superheating, this is your refrigeration effect. With superheating, this is your refrigeration effect. So you can see that refrigeration effect has increased because of superheating, and without superheating, this is your work of compression. Okay, H2 minus H1, and with superheating, this is the work of compression. Okay, and this will be always greater than this one. Okay, because we shall see later that these lines, the isentropes, they diverge as you move into the superheated region. Okay, you can see that they are diverging. As a result, H2 dash minus H1 dash will be greater than H2 minus H1. That is very evident from this TS diagram. Okay, so we have one positive effect, that is we are getting higher refrigeration effect, and one negative effect, that is higher work input. So ultimately, whether it is good for the performance or not, let us see that. Okay, so first let me summarize what I have discussed. A useful superheating increases both refrigeration effect and work of compression. It also increases, you might have noticed that by pushing the suction condition into superheated zone, the compressor discharge temperature also increases, and since temperature is increasing at the inlet to the compressor at a fixed pressure, the specific volume of refrigerant also increases. That means in addition to refrigeration effect and work of compression, superheat also affects the compressor discharge temperature as well as the specific volume of the refrigerant at compressor inlet. Okay, these are the effects. Okay, now whether the COP and volumetric refrigeration capacity or volumetric refrigeration effect increases or not depends upon the nature of the refrigerant and operating conditions. So you cannot say offhand whether superheating will improve the COP or not. Okay, it's very much a function of the nature of the refrigerant and also to some extent the operating conditions. Okay, so you have to examine each refrigerant and decide whether superheating increases COP or not. Okay. We shall see that a little later. Whether it increases COP or not, some amount of superheat is always used in practical systems to prevent entry of liquid into compressors. So there is a very practical reason why superheat is necessary in actual systems, because just like an expansion device cannot tolerate vapor, a compressor we have seen in the last class cannot tolerate, most of the compressors cannot tolerate the presence of liquid. Okay. So you must make sure that whatever is entering into the compressor is vapor. Okay, no liquid is entering into the compressor. Now if you have a cycle without superheating, that means the entry condition is on the saturated vapor line. Okay, and due to some changes in the evaporator load, it is quite possible that the entry condition can shift into the two-phase region. That means some liquid can enter into the compressor, which may damage the compressor. Okay. But if you are providing superheating, even if there is some small change in the evaporator load, still the exit condition will be in the vapor region only. So you are ensuring a safe operation of compressor. Okay. So this is one of the reasons why superheating is provided in almost all systems, whether it increases COP or not. And it is also seen that from practical observations and experimental results that superheating has beneficial effects on volumetric efficiency of the compressor. So because of these two reasons, superheating is provided. But how much superheating has to be given depends again upon the nature of the refrigerant. Okay. And as I have already mentioned, useless superheat is detrimental. Okay, so you must always avoid useless superheat. That means you must avoid heat transfer between the refrigerant and the outside ambient. Okay, in the suction lines. This is the reason why all the suction lines are insulated. That means lines going from the evaporator to the compressor have got to be insulated, so that heat transfer between the surrounding air and the refrigerant can be minimized, thereby minimizing the useless superheating. Right. Now let us look at the use of liquid suction heat exchanger. So this is a modification over the simple cycle. Now we have seen that you can provide certain amount of subcooling and certain amount of superheating using the temperature difference available between the refrigerant and the heat source and sink. Okay, but there are certain restrictions, as you have seen, that is restricted by the available heat source and sink temperatures, and also on the additional area that you are providing. Okay, and if you want certain amount of subcooling and superheating, that may not be possible always just by exchanging heat with the heat source or sink. Okay, so one way of ensuring required amount of subcooling and superheating is by using what is known as a liquid suction heat exchanger or LSHX. Okay. So that is what is mentioned here. Required degree of subcooling and superheating may not be possible if one were to rely on heat transfer between the refrigerant and external source and sink, and also if refrigerant at the exit of the evaporator is not sufficiently superheated. This is another reason why we need a liquid suction heat exchanger. If the exit is not sufficiently superheated, then it may get superheated by exchanging heat with the surroundings, which as you know is useless superheating. So a liquid suction heat exchanger can ensure required amount of subcooling and superheating. Let us see what is a liquid suction heat exchanger. Okay, a liquid suction heat exchanger is basically a counterflow heat exchanger in which the warm refrigerant liquid from the condenser exchanges heat with the cool refrigerant vapor from the evaporator. So let me show this. Okay, so what we have here is a system with a liquid suction heat exchanger. In the basic system we had only evaporator, compressor, condenser and expansion device. So in the modified system we have added an extra component, liquid suction heat exchanger. So what is happening in this extra component? In this extra component the liquid from the condenser, okay, liquid from the condenser is flowing in this direction, okay, and vapor from the evaporator is flowing in this direction. That means they are flowing in opposite directions, okay, and I will show you in the next slide that the temperature of the liquid that is entering into the heat exchanger is much larger than the temperature of the vapor that is entering into the heat exchanger. As a result, this liquid can exchange heat with the vapor. So the liquid becomes cooler and the vapor becomes hotter. Okay, that means if you look at the temperatures, T4, that is the liquid outlet temperature, will be less than T3 and T1 will be greater than T6. That means the liquid is getting subcooled and vapor is getting superheated. Okay, and as I have already mentioned, process 6 to 1 is superheating of vapor and process 3 to 4 is subcooling of liquid. Let me show this one on TS and PS diagrams. So what you see here on the top is the TS diagram and the bottom you have PS diagram. If you don't have any subcooling or superheating, or if you don't have any liquid suction heat exchanger, this is the temperature of the liquid, okay, and this is the temperature of the vapor. So you can see that a large temperature difference exists between the liquid and the vapor. So you can exchange actually heat between these two by using a liquid suction heat exchanger. That's what is happening here, that is what is shown here. Okay, so this is exchanging heat like this, okay, this is the arrow, this is exchanging heat like this. In this process this temperature is reducing and this temperature is increasing, and both the processes are typically almost isobaric. So they take place, this process subcooling takes place along the constant condenser pressure line, and superheating is taking place along the constant evaporator pressure line. Okay, the same thing is shown here also. So you can see that this is your process of subcooling and this is the process of superheating. Okay, this is your superheating, this is delta T, okay, delta T superheat, and this is your subcooling. So what is the effect of subcooling and superheating on the system performance? Immediately one thing is clear, that refrigeration effect has increased. Okay, without this liquid suction heat exchanger your refrigeration effect was this much. Okay, this is your delta H, or that is equal to QE. Okay, and because of this liquid suction heat exchanger now it has become this much. Okay, so that is a benefit, but you will also simultaneously see that there will be some increase in work of compression also, because without subcooling this would have been your work of compression, and with liquid suction heat exchanger this becomes your work of compression. Okay, so both the effects are present. Now let us write some basic equations for this. So what is the heat transferred in the liquid suction heat exchanger? If you apply steady flow energy equation and neglect potential and kinetic energy changes, then heat transferred in the liquid suction heat exchanger is simply given by this heat transfer. This is the energy lost by the refrigerant liquid, and this is that is equal to energy gained by the vapor. Okay, so this is for the liquid portion and this is for the vapor portion. and since the mass flow rates are same mass is flowing through both the components, this can get cancelled. So you can simply write this as H3 minus H4 is equal to H1 minus H6, where H3 is the saturated liquid enthalpy, H4 is the enthalpy at the end of the liquid suction heat exchanger, and H1 is the saturated H6 is the saturated vapor enthalpy, and H1 is the vapor enthalpy at the end of liquid suction heat exchanger. And if you are taking some average specific heat values, we can write this as CPL into T3 minus T4, which is equal to CPV into T1 minus T6, where CPL is the specific heat of the liquid and CPV is the specific heat of the vapor. And as you know, generally the specific heat of the liquid is much higher than specific heat of the vapor. That means CPL will be greater than CPV. So from this equation, T3 minus T4 should be less than T1 minus T6. That means delta T subcooling will be generally less than delta T superheating. Okay, how much less depends upon the values of Cp for liquid and Cp for the vapor. Okay, so that's what is mentioned here. Degree of superheating is greater than degree of subcooling, right? Now, if you define the effectiveness of heat exchanger as the actual heat transferred divided by maximum possible heat transfer. Okay, that means I am defining an effectiveness for the heat exchanger epsilon LSHX, which is defined as the ratio of actual heat transfer to maximum possible heat transfer rate. Okay, what is actual heat transfer? If you are writing it for the vapor, this is nothing but the m dot Cp into delta T of the vapor, that is m dot R into CPV into T1 minus T6. Okay, and what is the maximum possible heat transfer? The maximum possible heat transfer in a typical heat exchanger is for a fluid which has a lower m dot Cp. That means a fluid which has lower mass flow rate into specific heat will undergo the maximum possible temperature change. Okay, so as a result, in our case, the Cp of vapor is less than the Cp of liquid, whereas the mass flow rates are same. So vapor has the lower thermal capacity compared to the liquid. So if at all anything is undergoing the maximum temperature change, it has to be the vapor. Okay, so Q max is nothing but mCp of vapor into delta T max. Okay, that's what is written here. So you can see that this is the mCp of the vapor and this is the maximum possible temperature difference. Okay, what is the maximum possible temperature difference? When the exit condition of the vapor is same as the inlet condition of the liquid. That means when T3 becomes T1, that is the condition under which you get maximum possible heat transfer. Okay, again these two are get cancelled. So you have ultimately effectiveness is defined as T1 minus T6 by T3 minus T6. Okay, so you might have studied in heat transfer this thing. How do you evaluate effectiveness in terms of other design parameters? Now, if you take a hypothetical case where you have a perfect heat exchanger whose effectiveness is 1. Okay, that means this is equal to 1. If this is equal to 1, what happens? T1 will be same as T3. And what is T3? T3 is nothing but the condenser temperature. That means by using a perfect liquid suction heat exchanger, you can heat the refrigerant vapor from the evaporator temperature right up to the condenser temperature isobarically. Okay, that means when epsilon LSHX is 1, T exit of the liquid suction heat exchanger will be same as the condenser temperature. This gives rise to an interesting cycle proposed by Grindlay, and it is called as Grindlay cycle. Let me quickly show the Grindlay cycle. Okay, so this is what is shown. Grindlay cycle is shown on TS diagram. So what is happening here is this should have been a solid line. Okay. So again, as I said, we are using a liquid suction heat exchanger. So heat is transferred from the subcooled liquid to the vapor, and I am using a perfect heat exchanger. Okay. So when I am using a perfect heat exchanger, the exit condition of the vapor will be same as the inlet condition of the liquid. That means T1 will be same as T3. That's what I have shown in the earlier slide. And what is T3? T3 is nothing but your Tc. Okay. So I am able to heat the refrigerant vapor from the evaporator temperature Te right up to the condenser temperature Tc. Okay. Then what I have to do, still it is at the same pressure. Remember that it is still taking place isobarically. That means the process is pressure is still evaporator pressure only. Next process, as you know, is compression process. Okay. And what kind of a compression process here? This is an isothermal compression. Okay. 1 to 2 is isothermal compression, because you have already attained the condenser temperature. So, you have to compress the liquid isothermally from 1 to 2. Previously we had isentropic compressor. So, by using a perfect heat exchanger, you can have this kind of a situation where the isentropic compression is replaced by an isothermal compression. What is the advantage of isothermal compression? We shall see in the subsequent lectures that isothermal compression will give rise to lower work input. As a result, you get higher COPs. Okay, so this cycle is known as Greenley cycle. That means a vapor compression cycle wherein the isentropic